My name's Tom, I'm from a company called Lightbend. If you've never heard of Lightbend before, you're not alone, because we used to be called TypeSafe. Then we decided it'd be a good idea to rebrand ourselves, and now nobody has heard of us. But we're the company behind Scala and the Play framework and Akka, and the newest member of our family, which is something called Lagom, which is going to be the subject of my talk today. Now, nobody has ever heard of Lagom, and that's because the Scala version was only released just before Christmas. We just got the Scala API done, so that's why I'm here talking about it today. So, before I go on to talk about microservices, who here currently works on a monolith? Anybody? All right, my condolences to you and you. Who here currently works in microservices? Yes. All right, good. So, as we all know, monoliths are kind of old and busted, and all sorts of businesses are kind of putting them to one side because they have their challenges, specifically about how you scale as a team, all right? So it was fine when you had like 5 guys in your team, but now you have 200 developers all trying to contribute to the same source code. Obviously, that no longer works anymore, right? So you split it up into all the little bits. So happy days, microservices to the rescue, right? Well, yes, I like microservices. They're good. You can now scale your teams. You can scale your infrastructure. You can scale your services. You can all develop independently, and then you can all deploy at a time which makes sense for you, all right? So happy days, we're now in the sort of nirvana state of software development, kind of. But once you kind of try that, you realize, well, yes, it solves a whole bunch of issues that you have, but now you have a whole bunch more problems to solve because they're not a silver bullet. So you have challenges to do with the sort of DevOps side of things, so how are you actually going to deploy it and manage it and discover services and things like that. And so in recognizing these challenges, that's why we created Lagom. Now, Lagom, the sales pitch is it's an opinionated framework for creating microservices or something like that. And when I joined Lightbend, I read that, I thought, well, isn't that just bullshit, right? Because why do I need an opinionated framework when I have the Play framework, right? It's plenty opinionated. It lets you do microservices, right? Well, kind of. It lets you do a REST API, but it doesn't really help you integrate your services together. So Lagom was an effort by Lightbend to kind of take all the best bits, all the best practices that we think about in terms of Play framework and Akka, and kind of smush them all together, stick a nice API over it to make it easy for teams who are maybe not so experienced with microservices to get the best out of those tools. So all the stuff I'm going to tell you today, you can do that before Lagom with a combination of Akka and the Play framework, but we kind of try and put it all together to sort of force some consistency and to make it that kind of a little bit more accessible. So basically Lagom is a whole toolbox full of little bits to kind of smooth the process. But given that I'm kind of standing between you and your pizza, I'm only going to talk about one thing today, which is a thing called the persistent entity pattern. Okay, so as the previous talk alluded to, when it comes to scaling your microservices, it turns out that scaling your logic, that's quite easy, okay? You can just take your microservice and you can just shove it behind a load balancer, deploy a bunch of instances, round robin, Bob's your uncle, you've scaled your logic, okay? But scaling your data is hard, okay, because of a thing called cap theorem, which is going to bite you in the arse. So the canonical way of approaching this is with stateless over a data store, okay? So that's what most people kind of go with, and that's something like this, right? So we have our user, who I have the utmost respect for, as you can tell. We have our nice little service here, okay? So this is the thing that we write, and then we have, let's give us the best chance for success and say this is Cassandra, okay? So fantastic database, we really like it, okay, great. So in this instance, we're going to talk about sort of eBay kind of system. So your user comes in, places a bid on an item, okay? We read out the database, what's the current bid? Well, there isn't any. Congratulations, you have the high bid. Write it back to the data store, and then it gets distributed, okay? So now we're all good, and we're highly available, because it doesn't matter, you know, if one of these goes down, we can just read it out from another one. Okay, so that's all good. But then when we come to scale, we have applications that know nothing about one another, and we run into this problem, okay? So I'm sure you're all familiar with this if you've done any distributed computing, okay? They both read the same number 0 out, they both think they have the high bid, and then they both kind of replicate that to the data store, okay? So the default behavior is probably that Cassandra is going to do the last right wins. You could solve this a bunch of ways. You could maybe solve it with some sort of distributed locking or a compare and swap operation or something of that kind of nature. Or if you want to be really available, you could solve this by taking some compensating action later. So you could just kind of hope for the best and then if you realize that there's an issue, you take a compensating action. Obviously, that's not an amazing user experience for these guys because they each think that they've won it, right? But there's an alternate way of doing this. Rather than storing your state in your data store, which is the available way of doing things, you could store it in your actors, which is a more consistent way of doing things. We're choosing the C from cap, okay? Who's using Akka right now, right? Okay, a good few of you. So for anyone who didn't have their hands up, I'm going to give you a really quick fly-through of Akka, because it's this pattern that Lagom makes easy, okay? So in order to do that, I need some actors. Okay, here are some actors. At the heart of Akka, okay, you have some JVM process. Okay, here is our little JVM process, all on its own. It can have a REST API in front of it, or whatever you like, all right? And the nice thing about Akka is it's clustering, okay? So when a new application comes along, they know about each other. Unlike a stateless application, which are blissfully unaware of its siblings, they know about the other people in the cluster. And then your actors dangle off of that. All right? So your actor will live in one place in your architecture. It stores your state in there, and that will represent some sort of entity. It could be like a shopping basket or a customer's order or something like that. All right? So this kind of sounds eerily similar to a sticky session, which obviously is a bad thing, right? Because there's only one place in the system where your thing lives. So to combat that, we have a thing called sharding, right? So part of the Akka clustering is that when somebody joins, you instantly know via a gossip protocol where exactly in the system that guy is living, right? So you can go to any node, you can get a dumb as a box of rocks load balancer, go to any node, and you will always find the way to the actor that you are concerned with, okay? So that's good. So that resolves the kind of sticky session bit of it. The next cool thing about this is that it enables you to scale really easily. Because you have a cluster, you can just fire up a new JVM process anytime there's a surge in traffic. It will then communicate with one node, figure out all the other nodes in the system, and then the really nice bit is that thanks to sharding, those entities will just get moved to the appropriate node, complete with all the state and the logic together. The next cool thing is when, I know I'm going to talk about split brain later. I will talk about split brain. The next thing is when you get a split brain scenario. So if I can't talk to my node, right? So if there are a few failure scenarios that we have to cope with because we're on distributed computing. This could just run out of memory and die on its ass, okay? That's highly likely. What's also likely is that the network will let you down like it always does, and one or other of these will just fail, okay? So there's a feature of Akka called the split brain resolver, and there's features of clustering so that you can down your node. When that happens, its siblings react to this because it's all aware. They're all aware of one another, right? And it will move that along with the state and the processing to the appropriate place. And then any requests that hit one of these are just going to get sent to the appropriate location, right? Later, when it comes back, the reverse happens and it just gets load balanced back again. So, given that we have these entities which are now storing state in them, if we apply that to the same pattern that we had before, it goes a little something like this, right? So our two people come in. The nice thing about Akka is that these are linearized, so they're guaranteed to be fulfilled in order. So we get causal consistency in this instance. There's no inconsistency to deal with because you deal with the events one at a time. They will either succeed or fail. There's kind of no in between, right? And the compromise that you're making with this system, is that you don't have quite that same availability, but your ability to same availability. So you can get around that by the fact that you spread out the data for your system across a bunch of nodes. So if you have 10 nodes and one goes pop, it's only 1/10 of your users or your entities that are going to be affected. And because of the features around split brain and sharding and clustering, it will self-heal. So it's unavailable for a little bit, but it will come back in a matter of a few seconds. Okay, so after all that rambling talk, I'm finally going to actually show you some code. So Lagom basically at its core helps you implement this pattern. There are 2 bits to every service, right? So let's talk about our eBay kind of clone. I did this talk this morning, by the way, in Java, and I love the Scala one because it actually fits on one slide. So there are 2 bits to every Lagom service, okay? First of all, you define an interface, and then you implement that later, right? the interface is what you see here, and Lagom will actually automatically make a little client for you that you can invoke and call this stuff with. So we extend this service thing, okay, and that interface basically is just this function here. How lazy am I using a laser pointer? All right, so you define this descriptor, and this is basically smushing together a whole bunch of features and giving you a nice DSL for it. So this path call, this is a REST API, okay? So we can place a bid, and we can get the total bids for an item, okay? You define two functions. Well, you define a function for every one of these place calls, and the nice thing is it's type safe, okay? So when you place a bid, this is the model for placing a bid. It's got things like how much you want to pay for it, okay? And then this is a nice type safe collection of classes which say whether you're successful or not, or you've been outbidded or something like that. Similarly, when you get the bids, we obviously don't use the first parameter because this is a GET request, and we send back the list of bids. Okay, so far so good. The other cool thing with Lagom, which I don't have time to really talk about, is this thing. All right, so this is a REST API. That's synchronous. All right, I mean it's asynchronous in the fact that it uses futures and all that good stuff, but your consumer of this is still waiting on that response. This is an event stream, this is a topic. Behind the scenes, this is actually implemented using a Kafka broker. So we've decoupled those services, which gives you way better resiliency because you don't have that strong coupling in time. And it's the same sort of thing. So it's all lovely and type safe. And all you have to do is define that a topic exists, and then consumers can subscribe to that. Okay, so on the other side of this, right, you publish this, and we're working on a Swagger version of this right now as well, so you can abstract it even further. We give you kind of for free this way to call it, okay? So we'll automatically generate a little client. That's the service, that's the function that we want, and then you call invoke and you get a nice future back with the result. It's all nice and strongly typed, so you know what you're getting back. And it also has a circuit breaker built into it, right, which we have metrics to tell you when it goes wrong. So if you have an overloaded system, circuit breaker will trip, and then you contain the failure within it. So the more interesting bit is how you actually implement the guts of this service. So you have to essentially implement that interface, okay? So where are we? Here is the bidding service that we just defined. We are now passing in this thing called the persistent entity registry, okay? All that stuff I was just talking about actors and holding your state, this is the thing which knows how to look them up, right? So we just DI that in. There's a function down here which gets a type safe reference for your auction entity. So I know the number one requested feature of Akka is to make it a bit more type safe. Well, Lagom adds that type safety in. So you can't physically send, the compiler will kick you if you attempt to send this a message which this type, this auction entity, doesn't support. Right? So it catches it that step further. The sales guys insist I use the word guardrails, but you know what you're talking about, so I can actually use the proper term. So this is kind of a condensed version of our controller in play. Right? It will deserialize it for us. We get the entity, we use the ask pattern, and then whatever comes back, we map that onto the domain model that we're exposing in our interface and send that back to the client. Okay? The reverse here is, by the way, because we want it in descending chronological order. So that's basically it. And so your service definitions are really, really simple. It's just that little bit of wiring to go and figure out where the entity is. The interesting bit is what happens inside this entity ref over here. But before I go and talk about that, I'm just going to talk really quickly about something called event sourcing, which is our other best practice that we like to promote here at Lightbend. So one of the common patterns that we see when people use microservices is that they tend to distribute your application in space, but not in time. Okay, so they'll have their data center in like Singapore, and they'll have one in New York. And I used to flippantly say, when one of those gets nuked, business continues as usual. And with Trump getting inaugurated in a few days, you all need to start thinking about that seriously now. But they don't distribute it in time because they're coupled together. Any RESTful request, you're binding them together in time. So if one or other has a problem, then the entire chain has a problem. The more transitive dependencies you have, the worse it gets. But event sourcing can help that out. So we implement that in Akka. It's there right now using a feature called Akka persistence, and we give you a simplified DSL for doing it. Here's how it works. So we have our actor. The only way you can interact with this is by sending it a command, okay? This is for modifying the state or doing pretty much anything. The first thing that the actor has to do is validate it, okay? You can check that you're authenticated or authorized to do the command or check that it's valid or whatever. If that works, the next step is you generate some events. Now, unlike commands, events can't fail, right? They're facts. They're immutable facts in time, like this person definitely got the bid and he paid this much, right? Next, you persist it to your data store. And once it's at this stage, now you're in the happy place, because this actor can die horribly and we can resurrect that exact same state at this point. Beforehand, no problem, because the event wasn't applied. And when we do this, it's all nice and atomic, so it either happened or it didn't. You're not in an inconsistent state. Then you replay those events back into your actor and you mutate your state however you need to. Okay? The final step is you broadcast those events elsewhere in the system to anybody who's subscribing to it, for instance, in a topic. Right? This is how you decouple your systems. So what does that look like? Right, this is now the guts of Lagom. So we now have our persistent entity class, right? We're extending from that. That interface insists that you implement certain features. First of all, you have to define these types, okay? What the state looks like, what a command is, the superclass of your command, and the superclass of your event, okay? Those are the three things that a persistent entity cares about. It says, I need to know what the initial state is. In this case, it's you know, there are no bids, nobody has got the high one. And then we define a behavior, okay? This is essentially a state machine. The auction goes through phases, either it's not started or in the middle of it, or it's finished or we cancelled it, okay? Each one of these you then implement in this kind of little builder pattern, okay? So, first of all, let's say the finish bidding command comes in, all right? So when the command comes in to say stop the auction, it's over, first thing we do is we persist a new event like this, and when that's done and safe, we then reply back to the person who told us to do this to say it's happily done. Then at some point later in time, this will get invoked. So this event here, so this is an event handler, that is the same as the one we defined there. And the reason they're separate is because you can replay this. If your entity has just been moved around because the last one died, this is the only one that's going to get hit, okay? And in this case, we mutate our state. So we say now the auction has finished, okay? So this is how you get that resiliency, because you can rebuild your state at any point in time. So I'm kind of running out of time, and here is all the stuff which I wish I'd had time to talk about. So you can also do CQRS really easily, right? Command query responsibility segregation. That's where your read and write sides are different, because you can optimize them for different needs. We have publish subscribe, and it does full on back pressure with Akka streams. That's using Kafka behind the scenes. You get circuit breakers for free. On the command line, it's all really cool because you can just you define all the services you need. It will fire up all your services, it will reload them when you change any code. It will sort out Cassandra and Kafka for you, so you don't have to set up your data store or anything. Passivation is a really cool thing. Think of it like paging, right? So that's when you're done with a service or done with an entity and you haven't used it in a while. And it also has built-in service discovery, so you don't even need to care which port of service is running on. You just define that you need it, and it's wired up for you. So we are not hiring, but we are selling stuff. This is a thing called the production suite, okay? This is the thing that pays the mortgage. Basically, it handles the DevOps side of things, okay? So if you have a service defined in Play or Akka or Lagom, it has a whole bunch of tools in there for essentially deploying it, scaling up and down. You get consolidated logging. You've got monitoring taken care of, and that's where the split brain resolver lives, okay? So I think I'm out of time, and I have one question, I guess. Anybody? Go for it.
Why Java was not first release?
That's a good question. All right, so why Java, not Scala for the first release? Okay. As a company, we know we have a very loyal amount of followers who come along with us because they want to use Scala. Generally, those followers are the sort of people who would just have implemented everything I just said using Akka because it's fun, right? We are specifically targeting the developers who don't tend to do that, and those are usually the ones who tend to use Java more. The other reason is that Java is much more widely adopted compared to Scala. And finally, the Scala API was a lot easier to write than the Java one, and we sort of knocked that out in about 6 weeks, I think, whereas the Java one we had to kind of finesse a bit more. Okay.
We may have time for perhaps
One more. Okay, one more. Go for it.
Any plan to integrate with Swagger?
Yes. So that definition thing I just showed you, okay, that's built, you get a Java library that you can interact with. We want to abstract that away. So all of the stuff I just showed you doesn't preclude any sort of polyglot microservice infrastructure. If you want to call it from another language, that's absolutely fine. And the feature we're working on at the moment is Swagger integration. So essentially, rather than defining your interface and exposing that via a library, just a jar, we're going to expose that via a Swagger definition as well. So you have the choice, if you want to call it from some other language, that you can use that. Yeah. So have a look on our GitHub page. There is a bunch of demos on there using Lagom. And please, if you've got any feedback on the Scala API, we really want to hear it. It was released just before Christmas, and so we're dying to get some feedback on that.